I'll hand it over to Angela, and the floor is yours.
Thank you very much. For a second, I thought my computer had crashed, so I was about to panic. But it's really good being here and in this weird COVID world. As Vinny said, I was honored to finish my PhD at UQ, and my work was around bamboo and laminated bamboo. We were three, or are still three, that worked into that area. And I finished my PhD, and now I am working, as Vinny said, as a postdoctoral here at Melbourne in Monash. It's in a new lab called the Future Building Initiative, where we are looking into building, and in my particular case, looking into how technology and fire can start looking into developing new alternatives to create fire safe, autonomous, and advanced buildings. So without further ado, because today is Friday, I'll get started with my presentation. Hopefully, I'll be able to share my screen. Let me see if this works. And Vinny, I don't know if you are able to confirm that you're seeing my screen.
Yeah, it's perfect, Angela. Okay. Just a real quick note for all the participants in today's webinar. So at the end of the presentation, Angela has kindly agreed for her to answer some questions from the audience. So for those who do have questions, if you can please post it into the chat, and I'll curate them to Angela to answer. Thank you very much.
Thank you, Vinny. So I hope to put it in a nutshell, and I've tried to summarize a bit of my project. And my thesis is called Fire Performance Assessment for Design of Safe Bamboo Structures. And it starts with the motivation, and I think many of our projects are motivated because our society is pushing us in a very fast way to develop the tallest buildings, the fastest, the most energy efficient, sustainable, and most technological way. I come from the industry, and so I was able to see how much we did not prioritize safety and fire, and therefore we are including all of these novel materials without understanding exactly what are the consequences, just thinking that we know, and developing engineering bamboo products, which are great, aluminum composite products as well. But why are we doing this, and what can the consequence be for it? So bamboo is not necessarily a novel material. We have had it since ancient times. However, we have started to engineer our bamboo and looking it out and transforming it into very good materials, construction materials, such as the mats board in the picture that you can see in the left. And I'm going to turn my pointer, like the mats board or the oriented strand board, and screen board or laminated bamboo. And if you can see this picture looks very much like a timber beam or a COT or glulam, with the fact that bamboo has more small strips that are comprised with small, in this laminate, you can see very small strips that are glued together to become this big beam. And why are we introducing these materials now into construction? So for their structural performance in previous years, there has been an increased studies that have shown how great mechanical performance bamboo has. It has a high strength weight ratio, and it has been proven to some extent to be a bit better and compared with hardwoods rather than softwoods like Douglas fir, which we are using in our buildings today. Architectural loves also the finishing, and we are including them in products in our buildings like floors, ceilings, walls, facades, etc. With the good thing that it is a really fast growing grass that reaches maturity quite quickly, and therefore it's able to sequester 30% more CO2 than pine trees. So all of this makes it great. However, we are building with it without really understanding what are the fire behavior, the fire performance, and being able to characterize this material. So an example of this is the airport in Madrid. We see a beautiful ceiling here, all made of laminated bamboo. And in this case, a hotel in Amsterdam, where you have floors, ceilings, walls in this beautiful atrium. But what happens if we have a fire? Do we really understand how much time do we have for evacuation, and do we really understand how much time do we have for flashover? So we all know that for performance-based design, we need to understand and to guarantee that the available safe egress time is much, much, much greater than the required safe egress time. And we know that we are confident in following our fire curve for uncombustible structures, where we are able to know when the growth phase happens to design for egress before flashover happens. Then we are able to understand the fully developed phase and therefore design for the structural integrity of our structures. And to guarantee this structural integrity, we know that all load-bearing materials in a building must resist burnout. So we are having to guarantee that a decay phase happens. But now we are introducing, in previous pictures you saw that we are covering buildings with bamboo. And do we know if we are covering them for us or designing them to be fire-safe bamboo structures? So if a fire happened, what will be the behavior of during the growth phase, and what will be the flashover times? Will it potentially be earlier than what we had initially designed for? And so our people will not have enough time to evacuate, or potentially we are increasing the energy that our structure is receiving and therefore compromising the integrity of our structure in increasing the fully developed phase and increasing the energy. And of course, if we are looking into structural integrity, are we sure that this material will be able to decay? And if it will, when and under what conditions? So all of this brings new unknowns, and for us to be able to do a performance-based design, we do need to understand and start eliminating all of this interrogatory questions around what all of these unknowns are. So the main objective of this research was to establish the fundamental groundworks towards the performance-based design for bamboo structures. So this model was developed where, as previously we saw, we are correlating each of the different phases of the fire, the growth phase, the fully developed phase, the decay phase, accordingly to the parameters of the material, and characterizing our material in these terms. The growth phase, looking into the flammability parameters of bamboo. The fully developed phase, also understanding the thermal evolution and how this will occur inside the material, and looking into if we have self-extinguishment and hopefully achieving a decay phase, when and under what conditions that will happen. And we can see that this will potentially drive us to a performance-based assessment, but before, we need to also understand, and here in the left-hand side of the diagram, we need to include and start by generating the first information of the thermal characterization of bamboo to understand when pyrolysis, when the degradation of the material happens. And in the case of bamboo particularly, it's very important just because of what we saw earlier, the different and small pieces that we have inside one beam column, and to understand the different effects that adhesives can play as part of the input, and also the different orientations that the lamella may have as part of the inputs. With this, hopefully, failure modes then will be understood better and projected as part of future studies, as well as right now for this, the aim of this project was based on bench scale testing, and to really understand the dimensions of failure modes, we would need to scale up to medium and large scale tests that will potentially bring us for more information as well. So previous model is now turned into a methodology, and as shown before, it's divided into 5 main categories, where we start with the thermal characterization. In here we see the input model as well. The flammability, to understand and look into the growth phase and start building the curves and building the information that was lacking. The thermal evolution, looking into the fully developed phase and understanding how a bamboo compartment will, how much energy and how long will this take to develop before we reach self-extinction, hopefully, and if we do, under what conditions. Failure modes, again, in this project, it's just an initial hypothesis based on the information that we have, and to understand the difference of the components, we started testing 3 different types of bamboo. So the species chosen was only one. So all of the 3 different types of bamboo, all of them are from the same species, Philostachys pubescens. But 3 different samples were chosen to be able to assess and to be able to understand the effect of the adhesives. So sample A was manufactured with urea formaldehyde, polyurethane. Sample B, phenyl resorcinol formaldehyde, and sample B, phenyl formaldehyde. So initially, from the information of the provider, sample A is mostly used for linings and for covering bench tops and kitchens' internal designs. And sample B was obtained by a local provider here in Queensland, or over there in Queensland, here in Australia, used, and hopefully the provider was looking for external and structural uses. And the third material was acquired internationally, and this is what has been used mostly in most of the big projects where bamboo has been used. Again, as part of the model, we need to understand the effect of the orientation, and this is why during the process of the tests, the 3 different samples were tested on different size. Sample A, in this case, perpendicular to the grain. Sample B is also perpendicular to the grain. And sample C, and this is where I'll try to explain. Perpendicular to the grain in this space, as bamboo, you can see here, you can allocate it in a section where the strips, the small strips in this case, are located vertically, which is called edgewise section, or in this case, the strips are horizontally. This is how the manufacturers and commercially this product is sold. So we wanted to understand what would be the difference, if there was a difference between each of these two, or also the parallel when we have the heat either in this side, coming from this side, or from this side above. So I'll hopefully try to walk you through the different sides and orientations and along the way. So as a starting point, the input from the model, we started looking into the thermal characterization, and the pyrolysis temperatures were found using the thermal gravimetric analysis. And here, sample A, sample B, and sample C were tested for air and nitrogen. This is a test that is used to understand the degradation of the materials. So the tests are run in an experiment where you heat up at different rates. In this case, different rates, 1 degree per minute, from temperatures from 50 to 800 were tested. Then 5 degrees per minute, again from 50 degrees, finishing up in 800, 10 and 20, to be able to understand what was the different ranges and the different consequences of having several rates in each of these experiments. So here, all of these 3 samples, we can see that 3 different peaks are being able to observe here, and the peaks show the degradation that the material took place. So in this case, we see the first degradation peak, and thermal degradation peak here is because, and in most of in the 3 cases, around 50 to 100 degrees, which is caused due to the evaporation of the water. So the sample loses weight because it's losing and it's evaporating, and so you see a peak, an initial peak here. Then the second degradation took place in around 250 to 340 degrees. I am mentioning this range because this range is, again, from all of the different tests that were taken between 1 degree per minute and 20 degrees per minute, with the objective to understanding that range that we have of degradation in this spectrum. And the third different parameter or degradation was around 370 and 515. And this is due to the fact that bamboo its component are cellulose, hemicellulose, and lignin. And the degradation, from literature, you can read that the main degradation temperatures of cellulose is around 240 to 350, which is really in agreement with the second big peak, which is where the most amount of degradation happens. And the third, and lignin, degrades from 280 to 500 degrees, which is again in agreement to the second peak of the degradation, where we have the rest and most of the degradation. So from this experiment, the most important part of the findings was to understand the ranges in which bamboo degrades and the pyrolysis temperatures due to this degradation. Thermal conductivity was also determined as part of the characterization of the thermal characterization. And to look and to find the thermal conductivity, we use the hot disk constant analyzer. And this is a process, and you can see here, based on the use of a transiently heated plane sensor. You can see here we have a sensor, and this sensor is placed between two different samples, and the sensor conducts electrical impulses. Through the application of the electrical current, the temperature of the sensor is increased, and the resistance of the temperature is recorded as a function of time. So in this case, this TPS was able to perform this application of the electrical current and translate it into a thermal conductivity value. And you can see here the results comparing all of the three different samples. Sample A perpendicular to in one side, PP1, sample B perpendicular either in the, as I said, horizontal and then flat strip parallel to the grain as well. And we can see that for sample A, we see the smallest value of thermal conductivity, sample A perpendicular to the grain. And this is due to the fact that from all the samples, if we go back to the characteristics of the three different samples, sample A was the sample that had the lowest density, and therefore there are more air gaps inside the solid. And in this case, we see that the highest thermal conductivity is samples that were sample B parallel to the fiber. In this case, initially, we were expecting that sample C parallel to the fiber would also have a big difference compared to the sample C perpendicular to the grain, just like in similar like sample B. However, we are not able to conclude because this is right in between the error that we have. It's 0.1 greater, and this can be due to the fact that also sample C was the sample that had more, was more dense. Here, we wanted to put a reference and kind of to understand compared to timber, for example, what was the values of the thermal conductivity, and we can see that for oak and yellow pine, the thermal conductivity of timber is lower than the thermal conductivity of bamboo at ambient temperatures. We also did tests now still to understand the thermal conductivity, but at higher temperatures by using the same process, but now including this inside a furnace and driving the temperatures from 50 to 350 degrees. Again, parallel and perpendicular to the grain. And we have here the results for the three different samples. And if you look closely, you'll find that particularly for the samples perpendicular to the grain, in this case, the red dots are the ones that are perpendicular to the grain. Here, they show almost a steady state for the thermal conductivity until around 220, 225, 250. And then you start seeing a drop of the thermal conductivity after this. Again, and you can see it here after the test, you start seeing how the samples are charred, and therefore the lamellas have started to debond, and a lot of air gaps are now included. And this is why the thermal conductivity drops noticeably in this case. So to be able to characterize, we were not taking in consideration these values because this is not anymore bamboo, this is most likely char. And therefore, we averaged the values for the thermal conductivity from bamboo from 50 to 220 before the drop, which is in agreement to the tests from the degradation in the TGA before shown. And in here, we can see very clear the difference of the higher values of the thermal conductivity parallel to the grain compared to perpendicular to the grain. Just for the sake of time, going into the next part of the project, looking into the growth phase and looking into parameters for flammability. We started with the critical heat flux for ignition. Again, as part of the characterization, this is a lot of data that we were looking into. And the critical heat flux for ignition is very important as it represents the amount of energy that we need to reach ignition. So we used the cone calorimeter, and in here, the idea was to use heat fluxes from 10 kilowatts per square meter to 80 and start recording all of the ignition times. And in here, we can see the different heat fluxes at which we exposed the different materials. Sample A and B were exposed perpendicular to the grain to side PP1, and sample C was exposed to all the three sides. And in here, we are able to provide the recordings of time for ignition versus external heat flux. And where we see this asymptotic behavior, then it means that it's the minimum critical heat flux that we have before it ignites or for ignition. And so in this case, for bamboo, in perpendicular to the grain, the results found were 15. And you can see here that 15 was the critical heat flux found for all of the samples perpendicular to the grain. However, sample C, which was parallel to the grain, the only parallel to the grain test was given 14, which makes sense with what had seen about the thermal conductivity as well before. When compared to other timber materials, we are able to kind of have a baseline and understand where bamboo stands. And we see that bamboo has a higher or requires more energy to ignite when compared, in this case, the tests that were conducted by New, but with beech, radiata pine, and rimu, and they present lower critical heat flux for ignition. To understand another way to characterize ignition is through the critical mass loss rate. And this was run through the fire point theory to understand where are the points of ignition conditions in terms of the decomposition of the solid. And this means that when we are applying energy, volatiles and a lot of flow of volatiles start to gather. You can see here the mass loss, and when ignition happens, a steep increment of the mass loss rate happens when we have sustained flaming combustion. And in this here, then the recordings and the measurement of the mass loss rate for ignition is done exactly at the place just before ignition happens. And in this case, the value is measured accordingly. So again, we tested all of the samples, sample A perpendicular to the grain, sample B as well, sample C, and sample C also parallel to the grain. And in this case, and due to the way that the test is developed, we were not able to understand or to kind of develop any particular differences due to the adhesive or due to the if it's parallel or perpendicular. So results, particularly for sample C, did not allow to reach any conclusions to be able to separate if perpendicular or parallel was going to be importance for ignition. And so all of the data was recorded. And this is particularly important to to provide this information as well, because this enables professionals to, as part of the input for their design parameters as well. So again, comparing the results that we got with timber products and around and the critical mass loss rate for ignition is important to give it as a reference accordingly to the heat flux or temperature that was measured. So in here, you can see that for sample A, the minimum critical mass loss rates is 2 with a external heat flux of 17. So this was the measurement that gave the minimum, and the maximum for sample A at perpendicular to the grain. The maximum was 3.7, and for this, the heat flux that was tested for this particular result was 75 kilowatts per square meter. So usually the lower heat fluxes are the ones that are associated to the lower heat flux critical mass loss rates. As you can see here, the maximum mass loss rates in this particular case were given for at 75, 80 kilowatts, and 60 kilowatts, with mass loss rates of 4.5 over to 3.7, depending on the sample. But again, we were not able to find any particular trend, any particular behavior around any of the variables that we were trying to look. If we look around for timber, we see that the values also are quite all over the place, 5.1 and 2.5, 1.8. And this is why it's very important to characterize each material and to understand the different conditions associated to the external heat flux that is being measured by. For the heat release rate, it is a very important parameter that we need to obtain in our design. As we saw at the beginning, it's the energy that the material is releasing when it burns, and therefore it is very important to be able to measure and quantify how much this energy will be emitting or producing into a structure. So this determines the size of the fire and the amount of energy that our structure will receive. And therefore, in this case, samples, this is an example of the results for the heat release rate at 40 kilowatts. And it's important to highlight that at the beginning of the sample, when ignition happens, you have a high peak of heat release rate. And this is where you get the big flaming and the big measurement. But since we are dealing with a combustible or a char-like material, like bamboo, as soon as the material and as soon as the sample starts developing a char layer, you start seeing, in similar ways with the mass loss, that the heat release rate starts to decrease, and it starts to get into a steady state until it reaches what we call here, and this is a point of flame out. And so all of this, in this particular example, we have a peak, then we have a decrease while the char layer is formed, and therefore we have a insulated layer. However, after the flame out is gone, you are able to see here that there is still some heat release being emitted, and this is due to the smoldering combustion. So the only way in this particular test to be able to know that the heat release was over in terms of the setup of our sample was to remove the sample, and therefore we were able to guarantee that the conditions and the tests were returned to the baseline, which was 0 at the beginning, before having all of these concentrations of energy. So we measured and we put the different values in different stages, because first it's the peak value is high compared to the flaming steady state. And for this case, we did not, and for our test, we did not measure the smoldering combustion. So we just in our data, we just measured this part. And you can see here where you find in this values, the average heat release rate from that each of the different heat fluxes tested. And sorry, this is the average of the peak heat release rates that were tested. So the values are higher when compared to the average of the heat release rate per unit area in this for each of the samples. Sample B, perpendicular, sample C, perpendicular in both sides and parallel to the grain. In this case, you don't see sample A due to the fact that the adhesive that was used by sample A had experienced delamination, and we saw that earlier in the other picture where the lamellas had come apart. So the thermal wave reached the back at early stages of the test. So we were not able to validate our results because the heat layer, the thermal wave had already reached the bottom, and therefore we were not confident of these results due to the fact that that the bonding experienced this, that the wave reached the bottom in a quick way. So this is why we are only having sample B and C, perpendicular and parallel for sample C. Also, we are distinguishing these two values, just as I said before, because the peak heat release rate can be used for particular design methods, and then the average heat release rate is indifferent. Moving into the thermal evolution, and I'm gonna get faster. The in-depth temperatures and charring rates were tested for samples. We see here the delamination that I was talking about for sample A. And because of this, we were not able to validate or measure the charring rates or many of the information because of this behavior of the lamellas. And I think this is one of the highlight points of the importance of understanding what are the adhesives that we are including in the samples. Because if you have a product that you have this in early stages of a fire or even at elevated temperatures, then you automatically have it disintegrated, and therefore you don't have a solid beam or structure, and therefore this puts in danger your structure. So the charring rates were measured in the single isotherm approach, but also it was measured through the mass loss. However, I'm presenting today only the single isotherm because of time. And following up the isotherm that we found in the TGA earlier with the pyrolysis and the degradation temperatures. And so in this, we are able to present the charring rates, tracking the tracking the difference in the isotherm in 257, the 257 isotherm along the different movements in the sample. So the thermocouples were introduced, and we were able to notice and kind of to follow the depth of the char depth, and following in this case for 257 is what we are looking in here, the isotherm that is moving along and getting deep along the time of the evolution of the sample. And we see that similar to previous, the behavior where at the beginning we have a high charring rate, in this case sample C for at 80 kilowatts. In green, the orange shows the sample C at 40, this in perpendicular to the grain, and the blue line shows sample C at 15 kilowatts per square meter. These are the different tests. And we see that the charring rate for sample C at 80 is around, has a peak at 1.4, and then stabilizes or reaches a state around 0.8 and 0.6 for 80 kilowatts per square meter. For 40 kilowatts per square meter, it reaches a peak around 0.7 as well, and then it decreases around 2.5 millimeters per minute. And then for our samples at 15 kilowatts per square meter, you find not as much as a peak, but a more of a stable charring rate of around 0.35 accordingly in as for perpendicular to the grain. In this case, parallel to the grain, we find that for 80 kilowatts per square meter, the tracking of this isotherm and the charring rate, we have 1 millimeter per minute, and then decreasing again to around 0.6 as long as during the evolution of during the time. And then the orange shows the sample parallel to the grain at 40 kilowatts per square meter, reaching a bit more than 0.6 and then decreasing to 0.4 at the minimum. Similar sample, the sample tested at 15 kilowatts per square meter, then you have the 0.4 millimeters per minute, and then almost steady state in this case. More of the self-extinction, and to run with 10 minutes, the self-extinguishment test was also looked into as part of the firepoint theory, now looking into the critical mass loss rate, but for extinction. Similarly, that the critical mass loss rate for ignition, we before ignite, the mass loss rate increases in a steep way, and then as the mass loss rate decreases and the ignition extinguishes, you see that we start finding a steady state. Again, this is due to the two different regimes that we find when we have flaming combustion, and we found here that this is the moment where ignition stops, or sorry, not ignition, where extinction starts. And we have two different regimes of flaming combustion and smoldering combustion. In this case, we were able to measure where at this moment, just the burning rate and the self-extinction for flaming combustion. This is an example of a test at 19. And in this case, we are calling this the flaming self-extinction. And therefore, we are measuring that the mass loss rate for extinction in this example was 4 grams per seconds meter square. And this is the process that we follow for each and all of the different tests. Again, dividing into the, or defining that in this case, what we are measuring is the flaming self-extinction without looking into the smoldering combustion, as I previously mentioned. And as this is a second part or something that needs to be also studied in the future. So this is an example again of how it was calculated. This is the tests that were run, in this case for the samples run at 19 kilowatts per square meter. And you can see here the mass loss rate for self-extinction tract. Again, we have a big initial peak, and then we have a steady state. Looking into the rest of the either here we have the extinction. The dotted lines are where visually we were able to observe that extinction had occurred. And you see that after extinction, you have still the smoldering combustion that I was talking before, but under the measurements of the observation where extinction happened, then we are tracking and then understanding in this case that the mass loss rate for self-extinction was in this case 4.5 to 5 for each of the 3 tests. So these are the results that we obtained for the samples. And you can see that there were no, after were tested, all of the samples that were tested from 15 to up to 40, and we obtained critical mass loss rates from around 3 to 5.5, accordingly depending on the different type of sample, but there was no self-extinction after 40 kilowatts per square meter. So all of the samples that were tested for 40 and above, for 50 and above, all of them measured burnouts. So we were not able to observe extinction or flaming extinction. And therefore, this is the value that was set for critical heat flux for self-extinction for bamboo in this particular test, as there was no delamination was observed for sample C. And it's very important to say that all of these tests were conducted horizontally. So if you have a different set of tests tested vertically, this will potentially give different results, as again, we were talking about the delamination or the fall off of the lamellas, and this could potentially have a different result. But for the cases that we tested, all of them were tested horizontally, and therefore for our case, self-extinction did not happen after 40. Comparing values again to timber species, we are able to track that the mass loss rate for self-extinction at fire point was, for example, A, B, and C, 3.64, 4.5, and 3.37. There was not a particular differences depending on the orientation of the sample. And we can see here that for European spruce, pine, and particle board, we are not having, we are having similar values in agreement with the mass loss rate at fire point. And in this case, much of them are around 3.93, 3.48, which are similar to the mass loss rate at fire point for bamboo. They were, in this case, this measurement was at 30 kilowatts per square meter, that the test was at a heat flux of 30 kilowatts, and this particle board was at 35, and this European spruce was at 43.6, and these are the values of the samples tested at 40 kilowatts per square meter. So moving along into the fifth part of the failure modes. And again, just as part of what I said at the beginning, these previous sections from 1 to 4 are several or many different tests that are characterizing the properties and the parameters in thermal characterization, flammability, thermal evolution, and self-extinction to start putting data and to start looking into the the data that we need to provide for us to be able to build at as bench scale testing that we have. And now the idea of this section, and it's just to create like an understanding of all of the information that we have provided. Where does it stand and what's next? So we have looked into all of the different tests that I have just shown you, trying to understand still where we're at in this puzzle where we have so many questions, and we are starting to provide much more information. Now we know where ignition happens. Now we know under what conditions, and we know that self-extinction at this small scale are happening before 40 kilowatts per square meter. And so all of this information is just here in what we call the bench scale fire testing, looking into fundamental properties. But we now need, for this to scale up and for us to be able to create more knowledge, we need to do future works into what we call the full scale and looking into compartment and flashover in real scale testing to be able to validate what this model will look like. But in this case, and again, clarifying that to be able to look into higher scales, we need to understand and we need to develop more testing. I wanted to provide a bit of a reference from the bench scale test and looking into what would happen potentially, but just as hypothesis, and where does bamboo sits. So as an example of all of this data that I have just thrown into you, where does bamboo sit? And let me explain, this is a test that was run, oops, sorry, that's my alarm. There was a test that was run in a concrete building. So this is the Dalmarnock fire test. Most of you already know that they were conducted several years ago in the University of Edinburgh, and the results, and this is just the results that they provided, where there was a compartment that was ignited, and you can see here that along time, this is the average temperature rooms versus the time that this test run. So this does not have anything to do with bamboo. This was just a test that was run several years ago. And you had here that a sofa ignited around less than 100 seconds of the test when it started. Then you have that the sofa cushions ignited around 175 seconds. And so again, this is just the curve, the temperature curve that happened here. And we have here that the firefighter intervention came around where flashover started to happen, which was around 300 and 350 seconds. And this is the part where I'm saying, just as a reference, all of the information that I threw at the beginning, if we were going to say, what happened if we would have bamboo materials or bamboo lining in this experiment, with the data that we have now, we are able to say that potentially, and this is a hypothesis, bamboo would not be, or bamboo would ignite when the flashover has already happened. So what this is trying to say is that in this scenario, hypothetically, and again, we don't know this until we run an actual bamboo test, but just as a reference, it is interesting to include the parameter and say, okay, if this was my test, with now that I know that bamboo ignition temperature is around 368 to 338 degrees, then I would say that bamboo will be ignited along with all of the other things that were inside of the compartment. So not necessarily bamboo is going to be critical in the ignition part as part of the of ignition, and it will not contribute to early ignitions of a compartment. But again, this is just a hypothesis, and the idea of this today was just to provide a bit of a reference of what are the variables that, or where bamboo stands along in fire and in this sort of examples. Again, these tests are used as a benchmark, and we cannot direct conclusions, but this is just as part of what we are trying to give as an example. Another example in the same line uses as a reference a corner test that Zhang performed in 2018. And the idea of this is a surface that is uncombustible. And so this surface is included and it's subjected to a 30 kilowatt setup. So you'll have here a burner in the corner that will be providing 30 kilowatts as part of the test. And they tracked their heat fluxes measured along in these uncombustible setups that they had. So this is a wall, or these are like, this is a corner wall. So this is the corner, this is one side of the wall, and this is another side of the wall. They here put up burner that was emitting 30 kilowatts, and therefore they tracked with sensors the different heat fluxes that we're receiving around spreading in the wall. And this is a small one. These are small scale tests or medium scale tests. So again, just if this was or is uncombustible, and now if we were going to hypothetically introduce bamboo lining in these walls, what would potentially happen? Again, this is just a hypothesis, and this is a very, very, very simplified way to kind of to put in context the hazards of putting different materials without understanding their behavior. So assuming that we will have flame spread around these sites, we will know from now the data that we have that the fire or that the lining will spread, and assuming that we have only horizontal spread, that the area that this will abark is the yellow section. And therefore, if we have that the heat release rate per unit area is the mass loss rate times the heat of combustion, we know that with this, that the heat release rate is equal to the mass loss rate. Now we know a value of bamboo in a particular scenario, 3.5 grams per square meters. That will be the value that we are including now. The heat of combustion in this case is 19.4. And we are saying that this now has a value of 67.9. So what does that mean? That the heat release, which is the heat release rate per unit area times the area, looking into that orange or yellow area in this case, where we now have spread it and bamboo has released its energy in this case, then we will have an area of 0.73 meters per square, and therefore we'll have a heat release of 50 kilowatts per square meters. So again, the area is just associated to the value of where the spread has come. And we can potentially say, hypothetically, in this particular, using all of these simplifications, that bamboo will be contributing 50 kilowatts for this energy. So we initially started, the test had 30, and now bamboo has contributed with almost 50. So with all of these simplifications, we can see the hazards of changing a combustible lining that had nothing, just submitted to 30 kilowatts. And now just by changing the lining with all of the information that we obtained in the whole hour that I just dumped into you, and this is a very simplified, not tested, but it's just like numerically making a simple analysis, we are able to say that in this case, bamboo is increasing the heat release and putting in danger very much compared to the initial setup that we had, that was uncombustible lining versus bamboo lining. We are now increasing 50 kilowatts compared to the other. So again, the idea is to understand where we are standing and where bamboo stands when compared to not having bamboo and now including in our designs, and understanding the risks that we are putting by not designing correctly or putting things without the actual values. Again, I think that the most important part of this is that we need to continue this test, because these two examples that I gave you were more likely to understand what are the potential failures that we can have, and also understand that these hypotheses need to be verified or discarded by conducted tests that are with the same characteristics. So again, the idea and the message is there's more to do. This study has started with bench scale testing, small scale testing, and you will find Dr. Ian Pope looking into thermal behavior and heat transfer, not only in bamboo, but some of his work is in bamboo. So if you're interested in looking at that, we need to go now into medium scale for future studies. And Dr. Mateo has also looked into structural behavior, and I encourage you to look into both of them, of their work. But to really understand, to really assess what I have just in the two last slides, trying to challenge you, we need medium scale fire testing, and we need high full scale tests to be able to predict and to be able to design certainly. But we now have an initial part, but we're still missing the following parts of where bamboo. So again, as a concluding remarks and to finish up, these tests are only done for horizontal configuration, and there's a lot more to do for vertical configuration, because we have seen that the lamella, if you're using polyurethane, it's very critical because it falls off, it disintegrates, and therefore you stop having the complete solid mode. You have a burnt material and delaminated and fall off, and therefore the fire dynamics will completely change and the characterization will be different. More testing needs to be done to understand and lead into a better understanding of the heat transfer process, and that's part of what Ian has been looking. And Other types of engineering bamboo needs to be tested. This is just one laminated bamboo product, but as we saw at the beginning, there are many more products that are being used in construction, and therefore it's critical if just by looking at one, we are able to see the implications that it potentially brings, then we do need to look into the same framework for looking into new and other materials. I have finished, and I really want to again thank UQ Fire and the center feature timber structures for being my family and my day and night for developing this project, and Bamboo Moso and Yes Bamboo for also providing materials. I will stop sharing, and hopefully we are still in time. I don't hear you. You are mute.
Whoops, can you hear me?
I hear you now.
Excellent. Thank you so much for the presentation, Angela. It was fantastic, and honestly a very thorough characterization of bamboo from honestly every single aspect that you can possibly think of from the bench. So very good work, and it's great to hear about it. And I think it's quite pertinent and relevant right now with this big push to put in potentially combustible mass timber materials into modern structures. So very topical research. I guess we'll open up the floor to questions, and we've already received a couple. So the first one is from Dr. Felix Weisner, lecturer here at UQ within the FIRE group. And first, I guess he'd like to preface this by saying that he really likes the abstract examples that you've used to generalize the research problem. And then he asks the question: in the hypothetical scenario that you showed before, is the assumption of bamboo not igniting after flashover only based on the ignition temperature? How about what would be the influence of your thermal properties changing, or potentially of local ignition of bamboo from the flames?
Yeah, I think that's part of my point in emphasizing that we have to burn a bamboo compartment to be able to dig deep into it. There were some other references, for example, providing the heat flux value of 15, and we were able to do the large scale test in 2016, and so we had some values as well, or all of the large scale tests that we have done, and heat fluxes values also are quite high compared to timber, and so therefore we are hypothetically saying that bamboo will not necessarily be the first. So the hazard until now, we don't think it's ignition. The hazard is all of the other, the delamination, the fall off, all of the parts where we are seeing the increase in the heat release rate. But ignition in particularly, again, without knowing or without having a large scale test, we're not able to be certain for this, but ignition is not necessarily what seems to be the first problem, except with delamination and heat release and all of these other parts that I was mentioning. I don't know if that answers the question. So yeah.
Thank you. I'm sure if Felix wants to comment on that, he can send through something further. So just to continue, you've got another question here from Dr. Andrea Lucerini, currently a postdoc over at Ghent University and also a UQ Fire alumnus. So he says, thank you, Angela, for your interesting presentation. And what is the extent of use of bamboo currently for construction purposes? In which countries in particular is it mostly used, and could potentially be used to substitute other construction materials, and potentially what would it substitute?
So right now, codes don't allow bamboo to be used in high-rise building as structural members, but buildings are being built, and the initial examples that I showed were like the hotel that is covered in lining and ceiling and walls and floors, not as structural elements, but increasing and changing the fire dynamics of all of the compartments. Yes, these are examples in Europe, mainly the Spain and Amsterdam, and mostly they're pushing hard. There's a committee that are pushing hard to include this material as part of structural performance, like to be able to become structural elements in higher buildings, because it's been marketing and industry is pushing hard. And so I think right now the main source of these products come from China and are distributed to Europe right now. This is kind of the market where I have mostly seen. But still, for example, in Costa Rica, in Latin America, there are several builders that are using also as bench tops, linings, floors, but not as structural elements.
Thank you, Angela. And you have another question also from Dr. Martin McLagan, also a UQ Fire member. So he asks, he says, thanks for the fantastic presentation. It is a very wide and thorough characterization that you've done of bamboo. Have you considered any of the ISO room corner prediction models or anything of that nature? They have a whole range of materials, and in particular, they use cellulosic materials, which are very well represented in that configuration.
Yes, so there are so many things that you want to do. And at the beginning, my PhD, I was like very taking everything aboard. But there was a moment where I had to decide and focus what to take opportunity. And I think in agreement and coordination with my supervisors, and I think one was over there, it was kind of just to what are the main characteristics that we need to bring, and with what we have, to be able to provide at least the initial characterization and performance base, and from here building up into what you're saying. I think it's great, and there's several testing and opportunities to build, and I hope, if I could, to keep on doing. But for the sake of this project, it was limited to including the lift and flame spray that we had in the lab. Yep. But thank you for this insight. I think it's very good.
No, thank you, Angela. So it seems like those are all the questions were received. I've got one that I'd like to ask, and I guess it's a two-part question, which is, the first is the degradation, the TGA curves you showed were quite interesting, because you showed that you effectively have two different ranges for pyrolysis. And then what's quite interesting is that you seem to have a very narrow range when you have ignition, when you look at your bench scale calorimeter testing. So I found that very interesting. So it seems like you're very much controlled by the degradation and ignition of the, I believe, the lignin, which is the one in the small range, right?
Yeah, that's the peak. That's the highest peak. And yeah, I think that's mostly where it comes from. Still, yeah, the range, and like in the TGA, it was done from 1 to 20 degrees per minute. So I think we still have to kind of be ready, because fires, you don't know exactly how, when, and like but so that's why we wanted to do like the range of various.
Yep. Very, very interesting. And then the second thing I noted was you actually have a very large variability in the critical ignition mass loss rate within all your samples, particularly across the samples, which I guess could be quite problematic from a modeling point of view, and something that is quite concerning.
Yes, I think that part of that is all of the different, potentially the stages where I developed my test. I started in one lab, physically speaking, and finished them in another. That could have contributed of the locations. There was one set of tests that were completely run in the same setup, and I mean the same lab, physically speaking. But you know, these tests are visual. These tests have so much human error in it, and even if I was the most systematic or hoping to be very systematic, but you're trying to touch BC, measure, and in the same time, and you have like all of this data that comes along it. But yeah, that's why I put the error bars. So at the end, there was in particularly that question that you say, no conclusions to be drawn, no variability, no high, no lows, because the error bars were so big. But at least we have a range from 2 to 5 or 3 to 5, I believe. And that's the starting point as well.
Yeah, definitely. So I guess one final question, and this is from Dr. Felix Wiesner again. He asks, does the age of the bamboo at harvesting influence its thermal properties and flammability?
Okay, so that's a very good question. Right now, the tests that I have conducted are mature bamboo. And in this case, I don't think we will get products that are young compared to that. Mostly, and I would have to double check this, but mostly if you don't harvest it after 8 years, they technically go wrong for timber-like purposes. So they are usually the cutoff period. It's usually in the same, like from 6 to 8 tops. And so I think this is where the most likely materials that we have harvested age at this time.
Yeah. Okay. No, thank you so much, Angela. I think with that, all the questions seem to be exhausted. Yeah, so I'd like to thank you on behalf of the UQ Student Chapter for providing, for giving this talk and for educating us all a little bit about the bamboo space, and also about quite a bench scale flammability and the methodologies associated with that. It's very comprehensive work, and I have to admit, I feel a little bit overwhelmed with how much data that you've managed to accumulate and be able to synthesize and illustrate to all of us here. So excellent work, and we thank you for it.
Thank you for inviting me, and you know, now it's time to go to Red Room, or I don't know, where are we going now? I miss those days.
Yeah, definitely. Well, so for all the audience here, the presentation here, the recording will be uploaded to the UQ Student Chapter YouTube channel. So we'll try and get that done next week, and then we'll communicate the link over the appropriate social media channels. And if you do have further questions for Angela specifically, yeah, feel free to reach out to her. She has a webpage over on Monash University, so I'm sure if you Google her name, you'll have her email and you can correspond further with her. So with that, thanks everyone, and I hope you have an excellent weekend. Take care.
Nice seeing you, and thank you. Bye.